Thank you, Sabine, and thanks very much for inviting me up here tonight. And thanks everyone for coming out to downtown Sydney on a wet night. And thanks everyone who's online. I'll talk about hydrogen storage and salt. But first off, I'd also like to acknowledge the traditional owners. I live now in Canberra on Ngunnawal country, and that picture up the top there is part of our new rock garden in Canberra. And this is our Ngunnawal welcoming feature. 3 big boulders of Mount Painter volcanics with Indigenous motifs designed by an Indigenous artist sort of engraved upon them. And I feel this is a really lovely entry to the new National Rock Garden. And I must say, tonight you'll see me shoehorn references to the National Rock Garden in, probably more than I should, but I'm shameless. But I actually grew up at Mount Ku-ring-gai. I am a Sydney girl. And as I was a kid up there, right on the edge of the national park, I spent most of my childhood running around in the bush. And it was obvious to me right from those early days that someone had been there before me. And now we're learning more about this. And so I actually grew up on also the Eora Nation, but in Daru country. That's what they call northern part of Sydney, I believe. So that's just to set the long-term context of where we are and when we are. So this is work that I was actually, well, I think, I understand this is being recorded, but no one pays me money anymore, so I can say what I want to say. But there was a change of government and people asked me to come back to work on energy things. So there we are. So I came back to work on hydrogen to Geoscience Australia. And I tell you, it was just marvelous, sort of as a coda to my career, which had been very much in oil and gas, both working for Exxon and Western Mining and the government for most of the time, to come back and actually work on hydrogen, to repurpose those skills to being part of the solution rather than the problem. And there's still a large team at Geoscience Australia working around in low carbon studies, and hydrogen's part of that. So this paper was originally put together in 2003 and presented at what used to be the APIA conference, now called the Australian Energy Producers Conference, and it got the Best Paper Award. So I thought that was rather good. And I've updated it because, you know, things are always changing in this sort of space. But it's a very small part of the puzzle. So tonight I'd like us to think about how does this fit in a big context? And the big context is, how does hydrogen fit into an evolving energy future? Maybe can hydrogen fit into an evolving energy future? And then we know from our experience over the last couple of 100 years that to develop a new industry takes decades. So the question is, where are we along that path for hydrogen? Can we accelerate it? Is it worth going down this path? We need more alcohol to solve these problems here tonight. And the important one for us is, what's the role of the geoscientist in all of this? Right, so here's the big global energy picture. And, you know, I just, you know, for young people here, and it's wonderful to have an audience of young people. I tell you, the energy game is the biggest game in town globally. That's where the action is. And it really is exciting because it changes so much. So what's the orthodoxy 12 months ago is overturned. So if you want an exciting life, go to the energy game. So when you look at the global energy picture over, you know, hundreds of years, you see it's not so much a change in the energy mix by substitution. It's indeed addition. So we see this incredible increase, acceleration of energy use after the Second World War. Main driver of that is rising living standards and rising population. We understand now that in this century, we'll see global population stabilize and in fact, even perhaps decline. But energy use is not going in that direction. Are we going to see a step change in our energy demand with data centers and AI? Yeah. So the role of the geoscientists in helping feed the energy demand is a key one. So let's see how Australia fits in this. Well, one of the things I've worked on over a long time was where was the oil and gas in Australia, particularly the gas. And what we see here is from an early start in the 1980s, it took us 30 or 40 years to finally have that takeoff in about 2015, where we were producing enough LNG such that it was globally significant in the market. And if you read the engineering literature, this seems to be the mantra that you need at least 30 years to take a nascent industry to something that becomes to scale to be significant on a global scale or even a regional scale. So we've achieved this in Australia. But when we look back where we were in Australia in the 1980s, we knew the resource was there, the technology was there, and most importantly, the market was there. And indeed, the people who were selling the gas to, they became foundation investors in the development of those LNG fields. So can we replicate that? These are just things to keep at the back of your head as we now go into the geological detail of salt and hydrogen. You with me? Righto. So we're going to ask the question, why hydrogen? And then how does salt fit into this? So why hydrogen? Well, the idea is it can be very flexible. You know, this is why we've, been so captured by the fossil fuels, particularly oil and gas, because they're energy dense and they're flexible. Hydrogen perhaps can be like that, both as an energy storage and an energy carrier. And the particular thing is using it for these hard to electrified energy uses. And this is, the sort of the great white hope for Australia is, can we replace the fossil fuel exports in our economy with exporting value-added green steel and green iron? Certainly we have the resources here. My question is, do we have the vision and the persistence to achieve it? Again, we need more alcohol. Sorry. But where does the hydrogen thing and the salt fit in this? Well, I'm only talking about one tiny bit of the system. That's the energy storage and storing hydrogen. The whole idea is you produce hydrogen, green hydrogen, by using renewable energy, and then you store it. Not so much in a tank, but in fact in the subsurface. And really, hydrogen stored in salt caverns is a very competitive energy storage thing, much cheaper and easier than batteries. So it's interesting, the technology is always improving with batteries. For large scale, long duration and short duration storage of energy, hydrogen in salt caverns has a lot of advantages. So I'm leaving that there. And let's talk about salt caverns. So you're looking for a domal structure in the subsurface, which conveniently salt often forms in diapirs. And you want, it to be pretty much pure halite, NaCl, and you want about at least half a kilometre or more of it to be in a very sweet spot in the subsurface, because the confining pressures are important if you're storing gas. So you engineer these salt caverns by pumping fresh water down into your salt diaper, and of course it dissolves the salt, and then you pump the brine out. And this is a proven technology that's been used for decades in North America and Europe. And one of our co-authors on that paper was a guy from the US, and he does this for a living, storing gas in salt caverns. And they've got terrific deliverability, and they're relatively easy to make, and they can be cleaned up again by putting down some more fresh water. So it's a proven technology. So why is salt so good for this? Well, it's the deliverability, it's engineering things, as far as you don't lose much hydrogen used to taking it in and out of the salt cavern. And it's chemically inert to hydrogen. And of course, we know salt in the subsurface can flow like toothpaste. So it's ductile, so brittle fracture and losing things up fault is less of a problem. And we already have this decades-long industrial track record of doing this. So all sorts of different things are stored in these salt caverns, particularly in the Gulf Coast of the US. And when we're talking about the storage of hydrogen rather than, gas for heating, we already have several projects up and running. I don't know whether any of these are actually storing hydrogen that's been made from renewable energy with electrolysis or just hydrogen from natural gas. But this is one of the ways that we could actually take the carbon out of the energy system. And one of the really leading lights is here in Holland, this Etstel project. And of course, the whole North Sea is underlain by salt, the Permian zechstein evaporites, and plus there's Mesozoic and tertiary salt deposits all through Europe. So there's, a history right back into the Middle Ages and older of storing stuff in salt caverns in Europe. So it's an established technology. And then the question is, can we transfer that to Australia? Well, one of the questions is, and now really geological question for us geologists is, how does salt accumulations form? Well, I think you all know this. You just need to get some seawater and separate it from the ocean and then evaporate it, and you're left with salt. But as you evaporate it, you've still got to get the seawater coming in. So you've still got to have some sort of permeable barrier for that to happen. And if you evaporate a kilometre of water, you end up with about 17 metres of salt. And most of that will be halite. Now, we've all seen a bit of salt on the edge of a salt marsh. That happens a lot. And the majority of evaporitic environments in the in the geological section are these sort of things, which gives you shallow salt layers interbedded with carbonates and red beds. Not really what we're needing for our hydrogen storage. What we're looking for are these things down the bottom, these basin-centered, really large marine evaporites. And you really need very peculiar tectonic and eustatic and climatic conditions for these to form and to be preserved. And in fact, today, there's none forming right now that we can see at the big scale that we've seen at the past. Now, this is another important story for all you young people starting out. I did my PhD in Western Australia on Lake McLeod up north of Carnarvon. It's sort of an arm of Shark Bay to the north that got cut off early on by the growth of the Gascoyne Delta. And in fact, it's got a Holocene salt deposit in it, about 10 metres thick, which stretches over 100 kilometres. So, it's not really giant, but it is significant. And so I studied that, and I did that, and then I never used that work again until nearly 50 years later. And suddenly it's important to know where salt forms. And I did know that. And the trick to this, let me have a sip. The trick to this was Lake McLeod's cut off from the sea by the growth of the Gascoyne Delta, which is a little bit to the south, but cave systems in the carbonate barrier between it and the Indian Ocean, the Ningaloo Reef is out there, they pump seawater through the cave system to the salt lake, which lies about 4 metres below sea level. And it's the evaporation of that water which makes the salt. So very peculiar hydrographic conditions are required. And the other key requirement is you need an impermeable bottom In this case, it's a red Pleistocene clay. So, because as you evaporate your seawater, the brine that's left gets denser and denser and wants to seep away. So most of what you see in the geological section is red beds and gypsum, and most of the halite has already gone back to the ocean. So you need these peculiar conditions. But we know 5 million years ago, the Mediterranean, did this in spades. Enormous area of thick salt underlies the Mediterranean. Because, you had volcanic activity there around the Straits of Gibraltar. And we know today the Mediterranean climate is indeed hot and arid. And so it's evaporitic, all dries out. We see, if you've been to south of France, the valley of the Rhone is cut right down into its valley. Sea level didn't drop just by 100 or so meters that we see here with the Pleistocene. Back in the Pliocene or Messinian, the latest Miocene, it dropped by kilometers and kilometers. The Nile also cut down, and the Danube really entrenched, come down to these low base level, leaving these ponds of salt. And if you look at the distribution of the salt in the Mediterranean, a lot of it is only gypsum, because that's really what you get. And you only really get the thick bits of halite closer to where the marine source was, out to the Paleoatlantic and in the deepest parts. So this is telling us this is how these big salt deposits form. So this is a paleogeographic problem. So let's turn to Australia. How are we going for time? Okay. So where's the salt in Australia? It's mostly in the Proterozoic and the Paleozoic, mostly in central and western Australia. And we'll ask the question, is there any in New South Wales? Hopefully you can tell me. So when you look at the map, pre-Cambrian there, plenty of salt in the Officer Basin. The Amadeus there in Central Australia is there in lights in the yellow because it's got two really thick salts, one in the pre-Cambrian, one in the Cambrian. And then in the Paleozoic, all along those western margins of Western Australia, we've got some salt. And then over in Eastern Australia in the Adavale, we've got Devonian salt in the Adavale Basin, which is really interesting, I think. So we'll look first, of course, how do we find the salt? Well, you know this toolkit, well intersections, geophysics, of course, Mike, yes, the seismic, and indeed outcrop geology, because we always like an excuse to get into the field. And so this is an outcrop from the Proterozoic of the Flinders Ranges, and walked across it and I thought, oh, I've seen that before. I've seen that, in the modern at Lake McLeod. So that sort of crisscross pattern are the swallowtail gypsums left behind when they've been dissolved. So you can also use your outcrop geology. And it's all about repurposing the petroleum data, just as I was able to repurpose my, skills from the petroleum era. So let's have a look at the Tonian. Now, I didn't really know anything about the Tonian until I did this project. So, way back in the Neoproterozoic, and of course, this is the Centralian super basin. And we've got proven salt in the Amadeus, the Officer, and the Polda. We'll look shortly in more detail at the Polda there in the offshore. But we also think we've got salt way over there offshore Western Australia in the Bremer sub-basin. No wells ever been drilled in the Bremer sub-basin, but on the seismic, the deep water seismic, we see these strange diapiric features. So they probably are, I think, Neoproterozoic salt. I wish someone would go out there in the Investigator and dredge it. Yes, drill it or dredge it. Dredge it would tell you something, I think. Anyway, why is all this happening in the Tonian? This is work from Cyro and colleagues, yes. Rodinia, and as Rodinia breaks up, it creates the tectonic conditions that really help form these holes that you're going to put the salt in. and you see these salt deposits of this age, you know, in many places around the world. So that's Australia there. And one idea is, why does this happen? Is it because there's so much white salt flat glittering there in the sun that it increases the albedo and triggers a big freeze? You know, why do we get the snowball Earth? That's the next episode after the Tonian evaporites. Or other ideas are because of the Rhodinian breakup and tectonics, you get more weathering and it's a drawdown of CO2. Maybe over a drink we can talk about that. People may be able to clarify that for me. But I think that's a lovely idea. I just like the beauty of that idea. So let's go back to one of the ones that we've drilled. So this is the Polda Basin offshore South Australia, where we were out looking for oil and gas in the 1960s, and 3 wells were drilled. One of the mercury went through a kilometre of salt. And they just kept on drilling because they thought they'd eventually find oil, but they didn't. But we have this data now, and we have all the cuttings, not core, unfortunately, but you can get a lot of information out of the cuttings. So, and South Australia is very much, you know, the state government is very much in this space of thinking about green hydrogen. And they have a proven, very good looking salt diaper offshore in shallow water. But it's offshore, which is not insurmountable, because the hydrogen field in the North Sea that the UK people work on is offshore too, hydrogen storage area. But it'd be good if you could find it onshore. Now, this is why I thought this is a project worth doing. The back of the envelope calculation is you could create a cavern in a place like the Polda Basin by pumping fresh water down, and then put in hydrogen, perhaps that you've made with renewable energy onshore in South Australia, where you've got great renewable resources. And to create that cavern would be, we're talking tens of millions of dollars, and we're talking a year or so. And it would store more energy than Snowy 2.0. Yeah, so it's worth, you know, teasing this problem out a bit more. So the other question is, it'd be a whole lot easier if it was onshore. And of course, onshore South Australia, we've got rocks of the same age and wonderful field work done over the decades in the Flinders Ranges. You can see where all these salt diapirs have come to the surface. And I mentioned we can see it there in the outcrop as well. So that's an area that people are actively looking for. Can we find a place where you could create a salt cavern in onshore South Australia? And I wonder whether any of this extends into eastern Western New South Wales. No. Righto, let's move on and talk about the Devonian, because the Adavale is again where we've got salt, and perhaps in a more useful place than offshore South Australia. And we've had a big round of drilling again there back in the 60s and 70s, because the small Gilmore gas field was found. And at least half a dozen of these wells intersect salt. And in this case, they've caught it, and we've still got that core to look at, stored at Geoscience Australia and up in Queensland. And, you know, you can get terrific information out of the salt core. You really start to understand the processes. So we can see from our geophysics, we've got 3 main salt bodies, and we've got thick salt, and it's just at that sweet spot in the subsurface where having a cavern dissolved out would be a suitable place to store the hydrogen. And actually, Geoscience Australia next week is drilling up in the Adavale Basin. They're actually doing the top hole for a groundwater study, so going through the Eromanga. And the plan is to go back and then re-enter that hole and see if they can get into some of this salt. So things are sort of ticking over there. So paleogeography. So that's the Devonian stratigraphy. the Boree salt is the name of the salt unit in the Adavale. You can see the Adavale there on our, our historical artifact of our paleogeographic map from last century. And you can see it's a good geometry for putting in salt, a restricted marine embayment, and it's associated with carbonates and some of the classic salt basins in the Devonian of Canada. You have growth of the Devonian reef, which sort of bars the basins, and then the next episode is the formation of the salts. And we've had some recent dates from the Boree salt, and rather than sitting down there on top of that carbonate sequence, the idea is it's at the base of the Eaton Vale above it. So it's way up in the Franian than in the Gavetian, which I like a lot better. And here is a PhD topic, if anyone wants one, trying to unravel the control of Eustace on when evaporites form. Because I think this new dating really puts it in a very interesting spot in the Franian as far as rapid regressions and transgressions. And this lovely picture there of the Devonian fish, because I know we've got a paleontologist here. And this is where I shoehorned in a bit of information about our rock garden mine. So that's the Adavale Basin there with the red ring. In the yellow box is another one of these marine embayments in the Devonian, and that's the Broken River embayment. And we actually have a bit of that rock in Canberra. You can see someone there with a black backpack looking at it. It's white and grey, so that's the National Rock Garden in Canberra. And it's a beautiful rock. It's got these big megadont clams, which are larger than my hands. And it's one of the favourite rocks when people come and look at it. And we had a treasure hunt for young kids, and we told them they had to try and find a shell that was bigger than their hand, and they were climbing all over it. So it was,
Marita,
yeah.
I think the audience.
Yeah, I wish I was there.
Ah!
Did you find that? Well, we were.
Right. There you are. Well, I'm using your, yes, that's you. So who's in the black backpack? Well, don't loiter near the rocks because you'll end up in one of my slideshows. Terrific. That's great, Kevin. Great. And this is a slide that I pinched from my dear colleague, Sarah. But this is the sort of stuff I think we need to be doing, that every rock tells a story. So, key people into this pretty rock, because it is spectacular looking, and make them think about, well, what was happening on the seafloor 400 million years ago? Anyway, back to hydrogen in the subsurface. So my question is there any chance of getting some Devonian salt in New South Wales? Well, again, we have these series of marine embayments, and we see that sometime in the Devonian, the marine environments do get into the Darling Basin. But everything I've seen in the Darling Basin is a boring pile of red beds. Apart from the mineralisation at Cobar, I don't know, perhaps people can improve my opinion of the Darling Basin. Now, here's some paleogeographies. That top map is the one we made way back last century, and I've always detested that map because it makes no sense. Because we have the marine up there in the Georgina, and people brought it in from Antarctica. That doesn't work at all. So, Addie, I want a much better Devonian paleogeography, please. And I was talking to Patrick Smith last night, and we're talking about this Larapinta Seaway, which supposedly went from Eastern Australia all through Central Australia to the Canning Basin, which I really like the idea of in the Ordovician, but Peter Haynes, who really is a guru and knows what he's talking about from Western Australia, doesn't like it. But I think it could come and go. So I would really like this explained. Explain the marine and Devonian in the Georgina Basin, please. Or did a seagull drop it? Or are the paleontologists kidding us? And they'll say, oh, no, those fish were freshwater fish. That's paleontologists for you. Anyway, I've insulted enough people. So the conclusions are Australia does have thick halite. We've actually drilled it in our search for oil and gas, which has, put us billions of dollars ahead. We have the toolkit to find more. A great job for geophysicists. All these regional, continent-wide geophysical data sets we have now, they're ideal for searching for this. And it's all about repurposing the existing data sets, but more importantly, repurposing the skills and exploration strategies that we all know. And paleogeography is going to be quite key. So to go back to our questions and to carry on the debate. So how does hydrogen fit into the evolving energy system? I think the real sort of prize that's there is this green iron and steel. The resources were actually here in Australia, really high quality renewable resources to make green hydrogen. Can we get a suitable salt deposits in the right area? And you may not even have to go through the storage phase because you could be using the hydrogen directly into your smelting processes, is what people hope to do. So the question, I guess, is, does Australia have the vision and the perseverance to do that? Not my problem, it's up to the young generation. And these new industries are built over decades, as we've seen. So where are we with hydrogen? Well, Tony Wood from the Grattan Institute, who I like to read on energy policy, he said hydrogen's out of the hype phase and it's into the hard work phase. It very much is. And I'm really pleased to see the third hydrogen conference coming up next year. And of course, the geoscientist is only a small part of this puzzle. Most of the activities at the engineering and economics and social license phase, but the geoscientist has a really important role, and that is mapping the possibility of what could possibly be achieved. The idea that you could make energy storage for a fraction of the cost of, say, Snowy 2.0. But also, the other thing is there is natural hydrogen accumulations in the subsurface. Can we find them? I think we're talking 50 years plus there, but it does occur in the subsurface, and there's some wells in Africa where they do use it. And we're only just on the, it's very nascent, that activity. So painting, the opportunities is our role, but also very, very important, telling the decision makers the risk, the uncertainty, and the fundamental complexity of what's under the ground. Maybe Joe remembers this, but back in the early days of CCS, carbon sequestration, there was great disappointment when there wasn't a suitable sequestration site underneath the car park of the coal-powered fire station. Just the lack of understanding of what's beneath people's feet. That's why it's so important as a geological society to, get our stories out there. So of course we've got to end with the rock garden, and it's a great place to do it. So thank you very much for your attention tonight.
Amazing. Thank you, Marita. Questions from the audience?
Marita, yeah, hydrogen is supposed to be fairly difficult to handle because it leaks out of everything.
Yes.
Is there a possibility of using ammonia instead?
Yes, and I think CSIRO worked on this quite a lot. And that is one potential, and the idea is transported you know, just like we do LNG, but ammonia.
Yeah.
And that's why salt is a good sort of halfway house for storage, because it's one of the few materials that will hold the tiny molecule in there.
Oh, so you can actually hold the hydrogen in the, you don't have to have it as ammonia.
No, in a salt cavern, but to
Yeah.
transport it, say, to Japan or wherever it's being used. I think the Norwegians have recently experimented with, you know, transporting hydrogen, but you know, we're really at the stage of the very hard work and the engineering, particularly about the safety.
If people's interest, I know hydrogen can actually leak through steel.
Mm.
So it's
Yes.
fairly nasty stuff to deal with.
Yes.
Yeah.
That's why use it really as you make it, and to turn it into something like green steel. That would be the go.
Sure.
Fantastic stuff, Marita. Thank you. Couple of points. One is, yes, ammonia is the way to transport it, but that also leads to an enormous industry in fertilizers.
Mm.
So hydrogen is not only an energy fuel, but also globally important as a fertilizer. So the idea of storing hydrogen for that use as well is really, really important. What was my other point? Yeah, you'll have to come back to me.
Okay.
You can
What
ask
do
a
you think
question.
you
I'll
think
come
about?
back.
I love that so much, Marita. Thank you. Maybe I missed it, but there was you talked about the global tectonic setting, I guess, for the Tonian
Yeah.
and the rifting of Rodinia
Yeah.
and the production of all of the salt. What was the situation in the Devonian? Was there a global tectonic kind of a process that was driving salt, or is
I
it
guess-
more regional?
It's more regional.
Okay.
Yeah, and it's particularly where Australia is. You know, the
Okay.
top of Australia is still in the tropics in the
Yep.
Devonian, and you have these big marine embayments both on the east and the
on the
west, where you tend to get the salt.
Thank you. Oh, good. Okay.
Sorry. So the brines, when you're making a salt cavern, the brines that come out of it are going to be a problem,
Yes.
but they may also contain things like lithium.
Oh, yeah.
So is it? Do you think there's a potential there for value add?
Look, the
Such that-
lithium is mainly in non-marine evaporites. That's what the Atacama is.
Okay.
And all these salt caverns that we're talking about, the Zechstein and what have you, and all on the Gulf Coast, they're full on bona fide marine evaporites.
Right.
That's where you get the nice clean halite.
Okay. So, but you'd still have to deal with brines then.
Oh, you still have to deal with brines.
So that ESG piece then is really important, because you've got a lot of brines that you're going to have to deal with, and
Yes.
people are going to have to accept that and understand that.
Yes.
Turn it into table salt.
Yeah.
What can you do with that?
Oh, what would we do? Yes.
Jamie has a question at the back here.
Yeah, firstly, I'm so excited to see this presentation. So I worked on the Chandler salt for a decade. So
You would know the work of my.
yes.
Yes.
So I just always wondered, did you look at the Munter salt wall in the Officer Basin, the work by Peter Bolt? Because that's
Oh, yes.
That-
Well, the main person in the team, and it was a big team that pulled it together, was Mike, geophysicist. Anyway, he's on the paper.
Ah.
He did the officer work, and GA is still continuing there. We really put that over to the geophysicists, Mike. That was their part of the thing. I've really not worked on the officer since the 1980s.
But yeah, I think there's so much potential
Yeah.
in the salt storage across the country, because there's a lot of known, diapirs or salt
Yes.
beds that, exciting.
Awesome, thanks. Yeah, there was a question at the back here. I think there might be a question online, and then we'll close it up so we can have some of that alcohol to solve all the other problems. That's just thank you from John O'Lennon. Okay, well, Marita, this is just a small token of our appreciation.
Thank
Please join me in thanking Marita for all her amazing.
Yes.
We adore you.